Thank you. To stay on schedule, let's thank Chiara again. Philip, can you share your screen here? Yes. Okay, and now you need this microphone.
Is that all right? Can you hear me if I speak like that?
Yeah.
That works? Cool.
Okay, and
cool.
our last speaker of the session will be Philip, who will tell us about effectful semantics in 2 categories.
Okay, great. Thank you for having me. This is joint work with Hugo Paquet. The slides are online if you prefer to follow online as well. And what this work is about taking some structures which exist in computer science that we use for modeling programs and defining 2-dimensional versions of them. And here I've written 2 categories, but I couldn't fit 2-dimensional categories on the slides. But really, I mean bicategories. So up to isomorphism. Does that work? Which one is it? Down? There we go. So what I'm going to try and do is I'm going to start off by trying to tell you what all these different words mean, so you at least have an idea of why we care about these things and what the kind of work that we've done is. And then in the second half, hopefully we'll get time to tell you about some of the definitions and how they actually look. So let's start off with what effectful semantics is, because I'm not going to assume that everyone here is a computer scientist who does denotational semantics in the style that Hugo and I do. So what I mean by this is that we're interested in modeling programs. And the perspective we take on that is that a program is something that takes in some inputs, it does some work, and then it returns some outputs. And so there's a very natural way to think of that as an arrow in a category where you go from your inputs, you do some work, and then you have some outputs. So a simple example of that is this program here at the top. I've written in a kind of type theoretic notation. The way to read it is that it takes in some natural number, x, and it gives you back x plus 1. And we can think of this very naturally as a sort of function in sets, which goes from nat to nat, and it just is the successor function, right? So this is a very natural way to understand what this program is, but it's not a very interesting program, right? So the effectful bit is we're interested in programs that interact with the world. And what we mean by that, and sort of this word effects, what we mean by sort of things that interact with the environment or interact with the world or interact with the user. So things like printing to screen, interacting with memory, so you've got state in your program, non-determinism, so your program might be able to make choices and you've got no control over what those choices are, having some kind of probability. There's many, many, many different kinds of effects that you might have in your program. So to give one example, we can take our successor program that we had before, but now before it returns x plus 1, it's going to say print hello or print hi to the screen so the user can see it. And now if you want to interpret this as a function, we can't just go from natural numbers to natural numbers. We kind of have to remember that this printing thing is happening. And the way we record that is by going from natural numbers to the set of words or the free monoid over some set of characters. The product of that with the natural numbers, and what this function does, it takes the natural number and it gives you back the string hi as well as the natural number n plus 1. Okay, so when we're doing semantics, what we're doing is we're modeling programs as arrows in a category, but we want to think of them as arrows in some sort of slightly more structured category than maybe just sets. And the sort of structure that is there is going to be important. So if you sort of think of it in a sort of general, more abstract way, we've got written in this sort of type theoretic style, we have some inputs, gamma, and they all come with types. We have some effectful program, M, and we have some output type A. And we're going to model this as an arrow from the interpretation of gamma or the sort of meaning of gamma to the meaning of A in some suitable category. Okay, what do I mean by a suitable category? Here I mean something that's a Premonoidal category or a Freyd category. So here this is just a one-dimensional kind of point of view for now. And what are these and why do we care about them? Well, if you go back to sort of the 90s, 80s or so, there's all these different kinds of models that are all using all these different categories, and many of them they look quite different, and people are using them to model programs. Okay, so there's all these different sort of buzzwords up here, and it was first observed by Moggi in the late 80s that many of these could be described as strong monads on Cartesian closed categories, or just Cartesian categories. But this sort of point of view still doesn't quite capture all our examples, and so Power and Robinson introduced Premonoidal categories and then a little bit of a refinement of them in the form of Freyd categories. And the point is these algebraic structures provide a unifying framework for all these kind of models. So rather than just having to prove the same kinds of results again and again, we can just axiomatize that and work with these premonoidal categories or Freyd categories and prove results which hold for all the different models we might be interested in. And conversely, if I know my model is a premonoidal category or a Freyd category, I straight away know lots of facts about the way I can interpret programs in these categories. Okay, so we've got as far as effectful semantics, we've got as far as premonoidal and Freyd, and now I need to tell you why you might care about doing this in 2 dimensions, because you might just think we're just making life more difficult for no reason. But actually adding the second dimension is useful. It helps us give more refined semantics to our programs, right? Because now in a one-dimensional category, all I can say is my programs are equal or they're not equal. But if I have a second dimension, I can talk about them being isomorphic. I can talk about transformations between programs. And often, because bicategories especially are turning up from universal properties, we're really recording more information about our programs as we go. And so our semantics reflects that. So for an example of that, a familiar example of a bicategory, I'll give you a more formal definition later on, but here's one example, is that you can take spans. So you take a map from A to B to be a span, such as this thing up here, and you can compose these things by pullback. And if you look at what the pullback does, it's really doing the right kind of thing for composition. And the way we can think about this span is it's saying that rather than just A is related to B, we can say A is related to B, and I've got some witness in X, which tells me why they're related in some sense. Okay, so taking the spans perspective, we're recording more information, and so we can kind of see in our category why properties hold or how properties are true. But because this composition is pullback, and pullbacks are only associated by isomorphism, this thing is not a category; it's a bicategory. And you might think, well, okay, but I can always quotient spans to get a category, but then that's throwing away this extra information that we might be interested in. Okay, so the point of view we're going to take here is that we're going to take this kind of program that we had before, and instead of thinking about it as an arrow in a category, we're going to think about it as a one cell in a bicategory. And the kind of structure we're interested in is a similar version to the structure that we were interested in the one-dimensional setting. So one way to think about this work is there's all these different kinds of models of programming languages and other kinds of structures which have been introduced relatively recently. You don't need to know what they are, you just have to know sort of that they exist. They've been introduced for sort of lots of different reasons. And so once again, what we're trying to do is provide a unifying framework where instead of having to prove similar facts about all these kind of things about how we can model programs and program-like structures in them, we can just know that they have this extra structure and work with that structure instead. Okay, so that's the kind of end of the part about why we want to do this work. And so now the next part is I'm going to sort of move into some definitions. I'm going to tell you what the one-dimensional structures are, and then I'm going to show you how to sort of bicategorify it all. Okay, so let's talk about what it means to be a premonoidal category. So the starting point and the observation you need to bear in mind when you think about why premonoidal categories are defined the way they are is that programs matter in the way that we run them. Okay, so if I have a program that's print A then print B, that's clearly not the same program as print B then print A. Okay, because one gives you AB and one gives you BA. So these are two programs that are not the same thing. More generally, okay, if I've got programs P and Q that take in some variables gamma and some variables delta and give you back A and B respectively, then I can do two different things. So the first thing, I run P, and it maybe does some interaction with the world, but it gives me back some V, okay? And then I run Q, and it does some interaction with the world, and it gives me back W. So maybe it gives you back 2 and 3 or something like that. And then I give back to the user or the rest of the program this pair of values, V and W. And now if you interpret that in a sort of semantic point of view, thinking here in a kind of linear style, if you're sort of familiar with these kind of things, what this sort of program is doing is I've got gamma and delta. So you can think of that as sort of a list of both gamma and delta. And I'm running P first and ignoring all my delta things. And then I'm running Q and ignoring all my A's. And then I'm just pairing those up together into that VW. And that's not the same as running Q, running P, and then pairing up the results, which is, from a semantic point of view, running Q and leaving gamma alone, running P and leaving B alone, and then pairing up the results. okay? Because P might be printing A and Q might be printing B, and then the order of them is really going to matter. So if you draw these green arrows in a square, what you see is that another way to phrase this key point here that I'm trying to make is that interchange is failing, or the bifunctorality of the tensor product is failing. Okay, so this diagram here should not generally commute. So a premonoidal structure is going to have to take that into account. Okay, so despite this, there are some maps for which it will commute, right? And these are the ones, if P and Q never did any printing, right, they were just nice computer, nice sort of calculation values things. If they were what we might call pure or effect-free, or here I'm going to use the word values, then I could interchange them, okay? The problem was that P and Q were interacting with the world in some way. They had some effects. But if they didn't have any effects, then I can swap them and that would be fine. Or push them past each other and that would be fine. So this is what a premonoidal category axiomatizes. So we're going to have to build up the definition in stages, because what we're going to want is going to be something that's a bit like a monoidal structure, okay? But it's really only monoidal on the values, and on things that aren't values, we're not going to get a monoidal structure. We get something that's a bit weaker. So the first part of the definition is we start off with what's called a binoidal category, okay? And this is a category which is equipped with a tensor product on objects. Okay, this is not a functor. We've got a unit object, and then we've got, for every A and B, we've got things that want to be A tensor blank and blank tensor B, but because we're not functorial in both arguments simultaneously, they only exist on one side or the other, okay? So these two don't stick together to form a functor in two arguments. It's just what they ought to be if this was a tensor product in a monoidal style. Okay, so what I said before is that what we want is that we have something that's a bit like a monoidal structure, where the monoidal structure sort of lives in the values, in the well-behaved maps. And so I need to give some axiomatization of what those well-behaved maps are. And in a binoidal category, there are things that are called central. So the intuition here is the same as from rings, where the central elements are the ones that commute with every other element. So here, a map F is central if I can swap it with any G. Okay, so here I'm doing F and then G, and the other one I'm doing G then F, and it's likewise on the other side. Okay, so what you get for any binoidal category C, you get a category ZC, which is the center, and it's the category of the same objects and just the central maps. And so now the definition of premonoidal category is going to be a binoidal category. That's the first 3 points, 1, 2, 3. And then I ask for these natural isomorphisms like in a monoidal category, alpha, lambda, and rho. I take the same axioms as a monoidal category, the triangle and the pentagon law, and instead of just taking those generally, I need to ask for them to be central. So really they live in the center. And a consequence of this is that the center is monoidal, okay? Because on the center, the tensor is really a proper functor, because bifunctorality holds on the center. It doesn't hold sort of in general, but it does hold on the center. And these are natural isomorphisms that live in the center, satisfy the triangle and pentacle equations, and have all the right structure. So that's straight away the case that ZC is monoidal. Okay, so this is what a premonoidal category is. And the sort of motivating example for this, if you're familiar with sort of Haskell or with the interpretation of programming languages using strong monads, this fits into this framework. Okay, so a strong monad is a monad T equipped with strength, which is that natural transformation at the top, A times tensor B, A tensor TB into T of A tensor B, which satisfies some axioms. If you have this structure on a symmetric monoidal category, the Kleisli category is premonoidal. And you can see this quite easily if you look at what these two functors are doing. Okay, one of them does the Kleisli arrow on the right, on B, and then uses the strength. One of them does the Kleisli arrow on A, and then does something which is essentially the strength, but you have to swap and then apply the strength and then swap back. You can do something a little bit more general if you don't want to assume monoidal. You can do some extra things, but it's a little bit simpler to state in the symmetric. Sorry, you don't want to be symmetric. It's a little bit simpler to state in the symmetric case. But it's also quite easy to see if you sit down and work through some simple monads that these two don't generally satisfy bifunctorality. So this tensor is not generally going to satisfy an interchange law. For a different kind of example, if you're familiar with the gray tensor product, or the funny tensor product on cat, a strict premonoidal category is a monoid with respect to that. So one example of a premonoidal category is the category of endofunctors and unnatural transformations, by which I mean just families of arrows which don't satisfy naturality squares. They're just families of arrows between the functors. Okay, so the idea you should have in mind is that a premonoidal category is a monoidal category minus interchange, and it axiomatizes the structure of the Kleisli category of a strong monad on a symmetric monoidal category. The problem is, from a programming point of view, you sometimes want to work, especially, you want to also have your notion of what the values are lying around. And what you don't want to do is you don't want to take the center the whole time, because, for example, if your monad is commutative, then everything lives in the center. So if you're trying to model probability or something like that, then you want some handle on the fact that the computations are not all central things. You want to pick some subclass of the central maps. And this is axiomatized by a Freyd category, where one particular example of this is the map from a category to its Kleisli category, but more generally we can pick something kind of a subclass of the center, which will be sort of the one that we want from a programming point of view. So the definition is following. You take a premonoidal category, you take a monoidal category, and you take these to have the same objects, like the mapping from C into its Kleisli category. You take an identical object's functor between them, and you require the functor sort of factors through the center. So all the maps in V can be seen as central maps. So it's kind of axiomatizing the idea that they're all the values, the well-behaved maps. And J strictly preserves the premonoidal structure. So it takes the tensor to the tensor, the unit to the unit, the associated to the associated, and so on. Okay, this should be unsurprising, because this is why I told you the definition would be that this is the kind of classic example of the Freyd category. It's not the only example, which is quite important for when we're doing semantics, but it is like an important one to have. Okay, so we're now going to look at the two-dimensional version of all those definitions. And first I'm going to tell you what a bicategory is a little bit more precisely. It consists of some objects. We've got 1 cells, F and G, and between those we have 2 cells. And the important point is that we have associativity and unit laws for composition, which don't hold on the nodes but hold up to isomorphism, and those isomorphisms are well behaved. Okay, so we can draw our 2 cells between our 1 cells in this picture like this, and instead of having F following the identity here being equal to F, instead it's isomorphic. And I quite like Eugenia Cheng's point of view on this kind of thing, that you can think of these isomorphisms as in what sense this thing is true. Okay, so what alpha, lambda, and rho tell you is in what sense composition is associative and unital in this model. And so from a programming point of view, it's kind of telling you in what sense these properties hold. So just in general, it's sort of exemplified by that last slide. The passage from categories to bicategories is taking equations, associativity and unit laws in the case of the previous slide, and replacing them by isomorphisms. And then we have to ask those isomorphisms to be subject to equations themselves. And then the question is, what equations? And that's the really difficult bit. Okay? So for bicategories, we kind of know, because we know what the axioms are for a monoidal category, but really the work in what we've done here is trying to work out what the right set of equations are, because getting it right is difficult, and the history in the literature is really riddled with cases of people thinking they've got it quite right and not getting it quite right, and so on. Because what you want is you want your axioms to be strong enough to prove useful theorems, but not so strong that you don't get any examples, right? You don't want to rule out all your examples because you've got a huge number of equations, but if you don't have enough equations, you can't prove any theorems about them. Okay, so examples of some bicategories. Cat, in fact, any 2 category with functors and natural transformations. Profunctors has been an important one recently, generalized species, if you're familiar with those. Bicategories of spans. Relations can be seen as a bicategory. It's locally posettal. The para construction, bimodules over a ring, all these kind of things have turned up through this week already. But here I want to talk about a particular one as well, which is a kind of a version of the co-para construction in some sense. But I want to sort of present it from a different point of view. So what you can do, you can take this thing called a graded monad, which from a programming point of view, if we think of monads as encoding effects, then a graded monad is like I've got lots of different effects, and they're sort of stuck together in a way that they're all compatible with one another. Okay, so when I'm modeling my program might have different effects, and I can sort of pass between them in some sensible way. So by definition, all that is it's a lax monoidal functor, or an action if you prefer. But for an example of this, you can think of lists of length n. So it's a kind of refinement of the list monad, where instead of taking all the lists, I can take lists of length n, so I can kind of reason about how many paths I've taken so far, for example. rather than just taking it's some number n, I can say it's at most n, and start reasoning with that instead of a more fine-grained semantics. Here, what we're going to work with is strong graded monads, which are what you get by putting the word strong in the right places, and I'm not going to tell you anything more than that. But a strong graded monad gives rise to a bicategory, which is essentially copower, but I'm going to call it T because I'm thinking of it like a Kleisli bicategory or Kleisli category. So it has the same objects as C. The one cells consist of a grade E and a map from A to TE of B. So that's why I'm thinking of it as a Kleisli-like construction. And the two cells are regrading. So I've got a map F and a map G. Then a two-cell sigma is a map from E to E prime, such that the obvious diagram commutes. And composition is given like composition in the Kleisli category. You do F, you do T of G, and then you do your mu. Okay, so with that background set up, I'm going to tell you a little bit very quickly about Premonoidal and Freyd bicategories. So I'm just going to give you some words, and I'm not really going to tell you very much about them. So a pseudo-functor is a map of bicategories, so it's associative, it preserves identities and composition up to isomorphism. A pseudo-natural transformation is a map of pseudo-functors, and a modification is a map of pseudo-natural transformations. And the way to think about a pseudo-natural transformation is it's got naturality up to isomorphism. So again, the way we think about that is it's telling you in what sense naturality squares hold at each case. Okay, so we take this definition of binoidal category, we apply our recipe, and we turn it into a binoidal bicategory by just replacing those things with pseudo-functors. That's all very nice. Okay, so what about centrality? To deal with this, what you have to observe is that these maps F here are actually defining natural transformations. It's a little bit, you kind of have to squint a bit to see it, but once you've seen it, it's kind of obvious. It's kind of a very category theoretic thing in that sense. So what these squares are encoding is that F defines a natural transformation as on these two things at the bottom. And so when we bicategorify that, as usual, we replace a property with structure. And so a central one cell is a map F, which comes with some isomorphisms, filling these two squares, telling me in what sense naturality holds, that satisfy the axioms of a pseudo-natural transformation. So then we can define a premonoidal bicategory by taking the definition we had for binoidalness, and instead of having central natural isomorphisms, we do the bicategorical thing, which is central natural equivalences, and then we add in extra data similar to a monoidal bicategory and similar equations. And I've put a red triangle there just to warn you that there is a little bit of a subtlety there. It's not completely straightforward exactly how you do that. Okay, so we saw before that unnatural transformations, functors and unnatural transformations is premonoidal. A similar fact is true at the bicategorical level if you take unnatural transformations and just families of two cells. And similarly, this Kleisli-like thing, or this copower-like thing, if you prefer, is also premonoidal. And interestingly, this premonoidal structure is very similar to the premonoidal structure of a Kleisli category. So this was quite nice. Okay, so a Freyd bicategory. Again, all we do is we take the categorical definition and we sort of replace it with pseudo in the right places, which here is not very much at all. The subtlety is here in this bit where you have to say what it means to preserve premonoidal structure. So here it's up to a special kind of pseudo-natural transformation, which is a kind of a stricter version of one in some sense, and we have to add in some compatibility equations. And when we're doing this, we were very careful to make sure we covered all our examples, so that made sure that we weren't too strict. But also, we throughout this definition, there's a whole bunch of equations in it, and it's not entirely clear why you should believe that they're the correct ones. So what we did is we proved a theorem that showed that a version of a one-dimensional fact is true two-dimensionally, which gives us some kind of assurances that this is actually the right structure. And what I mean by that is, I should say, get some examples. I'm not going to tell you what a strong pseudomonad is, but you get a Freyd bicategory structure out of that. And similarly, this Kleisli construction defines a Freyd bicategory as well, where you take the discrete monoidal structure. So you turn C into a two-category in a very trivial way. Yes, so why should you believe the definition? Well, there's this one categorical fact that giving a Freyd category is the same thing as giving essentially a bimodular category, or what is it? I can't remember what it's called. But you've got the two actions on each other. Is that it? Yeah. You've got actions on the left and actions on the right, and then you have a strict map of actions. So it's what that means is that the associator becomes essentially the associator for the action, and so on. You don't need to understand the details for that. All you need to do is see that these two kind of look the same. Okay, so this is what we prove in the paper, is that giving a Freyd bicategory is giving a pair of actions, and these things commute up to icons, which are kind of a strict version of a pseudo-natural transformation. So all of this stuff on the right-hand side is very canonical, which gives us a good sense that that thing on the left, even though it looks a bit weird as a kind of categorical definition, is actually equally canonical, which is nice. Okay, so I'm just going to sum up. So what we've seen is that two-dimensional models, they refine one-dimensional ones. So when we're thinking about modeling programs, two-dimensional models are useful because then they can give you more information. We can ask more refined questions about programs. We can ask why things are true and so on. Bicategorical, premonoidal, and Freyd structure is sort of a step towards building a framework for understanding these kind of two-dimensional models all at once, so we don't have to prove facts about them one by one. And that the definitions we give in the paper, they capture the sort of examples you'd expect from the one-dimensional setting, and also there is a correspondence that matches the one-dimensional setting as well, which gives us some confidence that the definitions are actually correct and not just ad hoc. I'll just leave some sort of words for future work there and then stop and see if we've got time for questions. Thank you.
Any questions for Philip?
This box.
Thanks for the talk. Does it have to be monoidal bicategories? Because you're doing a lot of coherence here, and monoidal two categories also generalize monoidal categories, right?
So all our examples are monoidal bicategories. So yeah. They're weaker than that. So you could strictify a bit and use gray monoids. The amount of work involved, I think, is probably about the same. And we wanted our definitions to really cover the bicategorical examples. So things like games and linear logic, they're interested in proper bicategories.
True. Thanks.
We have an online question from Jamie. You can go ahead and unmute yourself.
Oh, yeah, thanks. Can you hear me all right? Thanks, Philip, for your nice talk. So you gave some nice motivation at the beginning, print A, print B, right, and so on. And then you talked about bicategorical semantics as giving us transitions between programs, right? So could you take that sort of example from the beginning of your talk and sort of promote it to sort of the context we're in at the end of your talk? How can we make our mental model of effects sort of more sophisticated to take account of this sort of new technology?
That's a good question. I haven't thought about it in any great detail. I think we were driven by these sort of examples coming out of pro-functor style models of linear logic. So one of the things I want to do is sit down and write a sort of syntax for this that looks more like a monadic metalanguage or something like that, and then we can start thinking about these questions a bit more. No, it's a good question. I don't have a really good answer for that.
But what if we had transformations on our strings or some symmetries on our strings or something like that? Was that the right sort of flavor?
Sorry, can you say that? I missed. What was the last bit you just said? You had transformations on our strings?
I mean, imagine our effects are in some more structured universe, right? Where our effects can themselves have equalities or transformations or symmetries. I mean, that would seem like a natural application of these ideas. Is that the right sort of idea, or is that not?
Yeah, really? No, I mean, that sounds sort of like that sounds like a good idea. What I haven't, yes, I'd have to sit down and look at a Kleisli bicategory for a nice effect and see how it actually looks. Yeah, okay. Yeah, thanks. I don't have a good example at the moment.
When you work it out, send me an email.
Yeah, I will. Yeah, thank you.
Any other questions?
Thank you for the talk. I was just wondering, people who spend a lot of time thinking about operational semantics of programming languages seem to have all sorts of different calling disciplines: call by name, call by value, call by push value, and so on. Does this framework apply to all of those, or does it only apply to some of them, or can it be adjusted to fit others? How does that factor in?
So the point of view you take with the Freyd category is very close to its call by value. Because you've got values and computations. Usually call by name models are quite different, but the motivation that we had when we were starting this was around dialogue categories, if you're familiar with those, which are and sort of models in which you can sort of get closer to having both call by name and call by value together in some sense, which are a bit similar to models of call by push value, where you've got these adjunction model-like things. So the starting point for this work was trying to get to that point, and we need to sit down and write what it meant to be a strong pseudomonad to get there, and then that drove us to write these definitions down. So I think hopefully we're going to get there at some point, but that's the next thing. Yeah.
Okay, thank you.
Still have a question, Mario? Okay, then let's thank Philip again and continue the discussion. Quite possibly at the pub.